Have you ever stopped to wonder what consciousness really is, or why the smallest particles in our universe, like electrons and photons, behave so strangely defying the rules of everyday life? Some scientists think these two mysteries might be connected. The theory of quantum consciousness suggests that our minds could operate on the same mind-bending principles that govern particles at the quantum level. In quantum mechanics, particles can exist in multiple places at once, and observing them changes their behavior. Could our minds work in a similar way with thoughts and ideas existing in multiple states until we focus on them? Could consciousness itself be a sort of observer affecting reality on a quantum scale? This idea challenges what we know about both physics and self-awareness. As we explore, we'll see how quantum mechanics and consciousness might actually be linked in ways we never imagined. Just looking at an object, like a cup on a table, doesn't make the cup act differently. But in the quantum world, things don't work the way we expect. Here, the simple act of observing a particle can change how it behaves. This puzzling idea is known as the observer effect. What exactly is the observer effect? It's a phenomenon where the state of a quantum system is altered by the active measurement. Think about it: why should observing or measuring something cause it to change? To understand this better, let's start with some examples from quantum physics when scientists measure the position of an electron. The electron's behavior changes. If they measure its momentum, that also changes too. So what's going on? Why does it seem like quantum particles react to being watched? One explanation is that measuring a quantum particle isn't as simple as taking a quick look in quantum mechanics. Measuring means interacting with the particle in some way. For instance, to detect an electron, scientists might shine light on it. But light, even in tiny amounts, carries energy. When that energy hits the electron, it changes its state. It's like trying to watch a leaf floating on a pond. By dropping a pebble into the water, the pebble disturbs the water and moves the leaf. So the simple act of observing affects what you're trying to see. But is it just about interaction, or is there something deeper? Something more connected to the nature of quantum reality itself? This question brings us to a concept known as the collapse of the wave function. In the quantum world, particles are described by a wave function which gives the probabilities of where they might be or how they might behave. Before you measure a particle, it exists in a superposition of states, meaning it's in multiple states at once, like being in several places simultaneously. When you observe or measure the particle, the wave function collapses and the particle settles into one definite state. Why does this happen? No one fully understands. Some physicists suggest that the act of measurement forces nature to make a choice, selecting one outcome from all the possibilities. Imagine having a deck of cards where each card is both red and black at the same time. When you pull out a card and look at it, it becomes either red or black. The idea of wave function collapse is also linked to one of the most famous thought experiments in physics, Schrödinger's cat. Here's how it goes. Imagine a cat inside a sealed box. Inside the box there is a radioactive atom with a 50 chance of decaying within an hour and a 50 chance of not decaying if the atom decays. It triggers a mechanism that releases poison, killing the cat. If the atom doesn't decay, the cat remains alive. Since the atom's decay is a quantum process, it exists in a superposition of decayed and not decayed states. And because the cat's life depends on the atom, the cat is also in a superposition, both alive and dead at the same time. Only when you open the box and observe the cat does it collapse into either being alive or dead. This thought experiment raises a simple yet mind-bending question. Is the cat really both alive and dead until someone looks? Or is there some hidden process we don't understand yet? Schrödinger used this example to illustrate how absurd quantum superposition sounds when applied to everyday objects, but it's also a way to highlight the impact of observation on quantum systems. Does this mean that consciousness itself plays a role in determining reality? That's another mystery. Some physicists have speculated that consciousness is key to the collapse of the wave function. They argue that the act of a conscious observer measuring a quantum system causes the collapse, but not everyone agrees. Many scientists believe that simple interactions with measuring devices, not consciousness, are enough to cause the collapse. Why does this matter? Because it gets to the heart of what quantum mechanics says about reality. If consciousness plays a role in quantum measurement, It could mean that our minds have a deeper connection to the universe than we realize. But if consciousness isn't involved, it still leaves us with the puzzle of why reality behaves this way. One interpretation of quantum mechanics that tries to address these questions is called the Copenhagen interpretation. According to this view, quantum systems don't have definite properties until they are measured. An electron, for instance, doesn't have a specific position or momentum until you measure it instead. It exists as a range of probabilities described by the wave function. Only when measured does it settle into a definite state. The Copenhagen interpretation emphasizes the role of measurement in shaping reality, but it doesn't explain why this happens. Other interpretations take different approaches. Some suggest that quantum particles are always in definite states, but we just don't have the full picture yet. The debate continues, and no single explanation has been universally accepted. If you think about it, quantum mechanics is like a giant puzzle with missing pieces. We have rules that work incredibly well for predicting outcomes, but the deeper why remains elusive. Is the universe fundamentally built on probabilities? Does the act of observing really shape reality? These are questions that keep physicists up at night. Another thought-provoking question: what role, if any, does consciousness play in the universe? If observing a particle changes its behavior, does that mean we are active participants in shaping reality, or is observation just a byproduct of how quantum systems interact with each other? The observer effect doesn't just exist in theoretical physics, it has real-world implications. Quantum measurements are the basis of technologies like quantum computing and secure communication methods. The more we understand about quantum measurement, the more we can harness these principles for practical use. But even with all our technological advances, the basic mystery remains: why does observing a quantum system change its state? In quantum mechanics, one of the most important concepts is superposition. Superposition refers to a state where particles like electrons or photons exist in multiple places or states at the same time. This might sound impossible, but it has been shown repeatedly in experiments. For example, an electron in a superposition can be thought of as being in several different locations at once, or having several different spins simultaneously until it's measured. Once it is observed, it collapses into just one position or state, no longer existing in multiple possibilities. To help understand this better, let's go back to the double-slit experiment we discussed earlier. When particles are not observed, they seem to pass through both slits at once and interfere with themselves, acting like a wave. This is a type of superposition where the particle is in a state of going through both slits at once. Only when we measure the particle to see which slit it passed through does it decide on one specific path. Quantum superposition is strange because it doesn't fit with how we experience the world in our daily lives. We see objects in one place at a time, not spread out across multiple places but at the quantum level. Particles don't follow this rule. Superposition challenges our sense of reality, suggesting that at a small scale things can exist in more than one state at the same time, only collapsing into a single reality when observed. Since superposition allows particles to exist in multiple states at once, some scientists have wondered if consciousness itself might be in a similar state. Could our minds somehow hold multiple thoughts, ideas, or even states of awareness at the same time? This might seem far-fetched, but some researchers believe that the human mind could work on principles similar to quantum mechanics, where our thoughts or perceptions could be superposed and not fully decided until we focus on them. Imagine making a decision. You may feel like you have multiple choices that are equally possible. It's as if your mind is in a superposition where you haven't yet settled on one option. When you finally decide, it feels like your mind collapses into that choice, leaving behind the other options. Some researchers think that consciousness might involve a similar process where different mental states exist together until a focus or choice brings one of them into reality. This theory is still very hypothetical, but it raises interesting questions about how our mind might work. Could our thoughts or mental states actually overlap, only settling into clear thoughts when we focus on them? If this is true, it might mean that consciousness operates on a level similar to superposition, where possibilities exist until awareness selects one. Quantum superposition could also offer insight into certain mental states such as creativity, intuition, or even decision-making. Sometimes, when people are being creative, they report feeling like their mind is open to multiple ideas or possibilities. It's almost like they're not bound to one way of thinking, but are open to many possibilities at once. This experience could be compared to quantum superposition, where all options or ideas exist together, and the mind hasn't yet chosen a specific one. Consider a situation where you're solving a problem. You might have several potential solutions in your mind at once, almost like different pathways. It's only when you focus on one of these ideas that you settle on a single solution. This way of thinking aligns with superposition, where the mind is open to multiple states or options until one is chosen. Quantum superposition could be a helpful analogy for these kinds of mental experiences, showing how we can hold various ideas or solutions in mind before deciding on one. Some scientists suggest that superposition could play a role in processes like intuition or gut feelings. Intuition is often described as an automatic sense of knowing without conscious reasoning. When people rely on intuition, it might feel like they're pulling from many possible thoughts or experiences at once rather than logically working through them. In this sense, intuition could be like a mental superposition where multiple ideas or bits of knowledge are present together, forming a gut feeling without a clear step-by-step process. Another area where superposition might be relevant to consciousness is memory and awareness. Memory allows us to hold past experiences in mind, but these memories aren't always active. They remain in a background state until something triggers them. This holding of different memories or pieces of information could be likened to superposition, where different memories exist together available, but not fully active until needed. Imagine trying to recall a specific memory, like the name of a song you heard years ago. It might feel as if the memory is almost there, with different parts of it coming into awareness, until you finally remember the name. In this way, the mind might be in a superposition of different possible memories, with one eventually coming to the surface. This idea doesn't mean that our memories are quantum states, but the concept of superposition could help us understand how different memories are present in the mind and become active when recalled. Some scientists believe that superposition might help explain states of awareness too. For instance, when we wake up from a dream, there's often a brief moment when reality and the dream world overlap in our minds. This in-between state could be similar to superposition, where both realities exist together, fading only as we fully wake up again. This is not to say that awareness is a quantum state, but the analogy of superposition could help explain these complex mental experiences. The idea that consciousness could work through principles like superposition is intriguing, but it's also highly controversial. Many scientists argue that superposition is a strictly quantum phenomenon with no application to the brain or consciousness. They say that quantum effects are so small and delicate that they're unlikely to survive in the warm, wet, and noisy environment of the brain. Superposition and other quantum phenomena usually require highly controlled conditions like those in a laboratory. Another criticism is that there's no clear evidence linking quantum superposition to brain activity or mental states. Neuroscience has made significant progress in understanding how neurons communicate, how memories are stored, and how different areas of the brain contribute to perception and awareness. So far, none of these findings suggest that quantum superposition plays a part. Critics argue that we should focus on what we know from neuroscience rather than speculative quantum theories when studying consciousness. Some scientists believe that concepts like superposition are simply being used as metaphors for consciousness. They argue that while superposition is useful in explaining quantum systems, it doesn't necessarily mean that the mind works the same way. In their view, comparing consciousness to superposition may be an interesting idea, but it doesn't provide any scientific explanation for how the brain functions. Despite these criticisms, the idea of superposition and consciousness continues to be explored. Some researchers believe that even if the brain doesn't function like a quantum system, the concept of superposition can still provide new ways to think about the mind. They see it as a tool for exploring mental states that don't fit easily into classical ideas of one state at a time. While we may never find direct evidence of quantum superposition in consciousness, these ideas encourage us to consider new ways of understanding the mind. Have you ever wondered if two things could be so connected that no matter how far apart they are, what happens to one immediately affects the other? In the quantum world, this isn't just a wild idea, it's reality. This strange connection is called quantum entanglement. But how does it work and why is it so puzzling? Let's start with what quantum entanglement means. When two or more particles become entangled, their properties are linked even if they're separated by vast distances. This means that measuring the state of one particle instantly changes the state of the other, no matter how far apart they are. It sounds almost magical, but it's one of the fundamental aspects of quantum mechanics. Imagine you have two entangled particles A and B. You take particle A to one side of the universe and particle B to the other side. If you measure the state of particle A, you'll know the state of particle B immediately. It doesn't matter if there are light years apart. This instantaneous change defies our understanding of how information should travel according to classical physics. Nothing can travel faster than the speed of light, yet entanglement seems to break this rule. How can two particles communicate instantly, defying the cosmic speed limit? Albert Einstein famously called this spooky action at a distance. He struggled with the idea because it seemed to violate the principle that no information can travel faster than light. But experiments later showed that entanglement is real and can't be explained away by hidden variables. The particles really are connected in a way we don't fully understand. How did scientists prove this? This brings us to Bell's theorem, a groundbreaking discovery by physicist John Bell. Bell developed a series of experiments to test whether hidden variables could explain entanglement. The results showed that no classical explanation could account for the behavior of entangled particles. These experiments proved that quantum mechanics doesn't just describe our world in terms of probabilities, but also implies a deep and unavoidable connection between particles, no matter the distance. Bell's work left no room for classical hidden variable theories. Instead, it confirmed the non-local nature of quantum mechanics. This raises some big questions. Does the universe have a built-in connectedness that we don't understand? Is reality itself more unified than we think? Quantum entanglement challenges our ideas of separation and distance if two particles remain linked over unimaginable distances. What does that mean for our understanding of space and time? It's a mystery that physicists still grapple with today. But entanglement isn't just a bizarre curiosity. It has practical applications. Quantum cryptography uses the principles of entanglement to create ultra-secure communication channels in quantum cryptography. Any attempt to eavesdrop on the communication disturbs the intertangled state, revealing the presence of an intruder. This makes quantum cryptography incredibly secure, which is why it's being developed for future communication networks. Another application is in quantum teleportation. No, it doesn't mean teleporting objects like in science fiction. Instead, it refers to transmitting the state of a quantum particle from one location to another using entanglement. Scientists have successfully teleported quantum states over significant distances, which could lead to breakthroughs in communication and information transfer. One of the most ambitious ideas being explored is quantum computing. Quantum computers use entangled particles to perform calculations at speeds that are impossible for classical computers. Entanglement allows quantum computers to process vast amounts of data simultaneously, thanks to the phenomenon of superposition and linked quantum states. The quantum computers are still in their early stages, but they have the potential to revolutionize fields like medicine, artificial intelligence, and cryptography. If entanglement is so strange, why doesn't it affect our everyday lives? The answer lies in a concept called decoherence. Quantum effects like entanglement are delicate and easily disrupted in the everyday world. Particles constantly interact with their surroundings, causing quantum superpositions and entangled states to break down. This is why we don't see quantum and entanglement influencing our macroscopic reality. It's a phenomenon that primarily exists in the isolated and carefully controlled environments of quantum experiments. Entanglement also raises questions about the nature of causality in classical physics. If you change something here, it affects something over there in a predictable way. Cause and effect make sense. But with entanglement, there is no clear cause in effect in the usual sense. The connection between particles isn't one of sending a signal from one to the other. It's an instantaneous change that happens to both. This challenges our understanding of how the universe works and whether space and time are as straightforward as we think. Another big question is, does entanglement imply that everything in the universe is connected in some hidden way? If two particles can remain linked over vast distances, could there be a web of connections throughout the cosmos? This idea has intrigued physicists and philosophers alike, though we don't yet have the answers. Quantum entanglement is also being studied for its potential impact on quantum networks. These networks would use entangled particles to create secure, fast communication systems. They could transform how data is shared, making it impossible for hackers to intercept information without detection. Despite all the strange and promising possibilities, entanglement remains a mystery. It's one of those quantum phenomena that forces us to rethink our basic assumptions about the universe. Is space as empty and separate as we imagine, or is it filled with invisible connections? If entanglement is real and fundamental, could it point to a deeper level of reality we haven't yet discovered? While some interpretations of quantum mechanics suggest that entanglement could hint at a hidden order or even a new way of understanding reality, we haven't reached a consensus. What we do know is that quantum entanglement challenges the classical worldview, opening up questions that we are only beginning to explore. Consider this: if particles are connected in ways we don't fully grasp, what implications might this have for the future of science? Could understanding entanglement unlock new technologies or even new physics? Or does it show us that the universe is far more complex and interconnected than our current theories can explain? It's a question that keeps physicists and thinkers endlessly fascinated. Entanglement is more than a quantum puzzle. It's a window into the mysteries of our universe, revealing just how little we still understand about the fundamental nature of reality. Have you ever thought about the implications of living in a universe governed by such strange quantum rules? If quantum fields and virtual particles form the foundation of reality, it challenges our understanding of what is real. Are we just observers in a quantum sea, perceiving patterns that arise from deeper fluctuations? Despite the many unknowns, the concept of virtual particles provides a crucial link between quantum physics and cosmology. It gives us a glimpse of how the smallest quantum effects can influence the largest structures in the universe. It shows that even empty space is more complex than we imagined, full of invisible activity that might shape everything we see. So as you think about the universe and everything in it, remember this: the seemingly solid world around us is shaped by forces and particles that defy intuition. Even the most empty places are buzzing with quantum activity, suggesting that reality is richer and more mysterious than we ever thought. Have you ever thought about how walls are meant to keep things out? It feels like a simple truth. If there's a barrier, it should stop anything from passing through. Yet in the world of quantum mechanics, this isn't always the case. This is where the strange phenomenon of quantum tunneling comes into play. Imagine you're rolling a ball up a hill. If the ball doesn't have enough energy, it will roll back down without ever making it to the other side. That's how barriers work in our everyday world. But what if the ball somehow appeared on the other side of the hill with no apparent reason? This sounds impossible, right? Yet at the quantum level, particles do something very similar. They can pass through barriers that they seemingly shouldn't be able to cross. How does this happen? Quantum tunneling is a result of the wave-like nature of particles. When we think about a particle like an electron, we usually picture it as a tiny solid object. However, in quantum mechanics, an éleron can also be described by a wave function. This wave function represents all the possible places the electron could be when this wave function reaches a barrier. A part of it can continue to exist on the other side. This means there's a small probability that the electron will tunnel through the barrier instead of bouncing back. You might wonder, why doesn't this happen in our everyday experience? The reason is that quantum tunneling is much more noticeable on extremely small scales, like with electrons or protons. Larger objects, like tennis balls or humans, have almost no chance of tunneling because their wave functions don't behave the same way. So while tunneling is a common event for tiny particles, it's practically non-existent for the things we see and use daily. Quantum tunneling isn't just a bizarre theory, it has real-world applications. One of the most famous examples is in the Scanning Tunneling Microscope, STM. This device uses tunneling to produce incredibly detailed images of surfaces at the atomic level. Here's how it works. A very fine tip is brought extremely close to a material electron's tunnel between the tip and the surface, creating a current that depends on the distance between them. By moving the tip across the surface and measuring the current, scientists can map the surface with astonishing precision. But tunneling isn't just useful in microscopes, it also plays a crucial role in nuclear fusion, the process that powers the sun. In the sun's core, temperatures and pressures are unimaginably high, yet even under these extreme conditions, protons don't have enough energy to overcome the strong repulsive forces between them. Instead, quantum tunneling allows these protons to get close enough for fusion to occur, releasing the energy that lights and warms our world. Without tunneling, nuclear fusion wouldn't be possible, and the sun wouldn't shine. Another area where tunneling is significant is radioactive decay. Some unstable atoms emit particles spontaneously, and tunneling is part of this process in the nucleus of an atom. Particles are confined by a potential energy barrier. Quantum tunneling allows some of these particles to escape, leading to the atom's decay. This decay process helps us understand how certain elements change over time and is important in fields like geology and archaeology. Does quantum tunneling mean that all barriers are meaningless at the quantum level? Not exactly. The probability of tunneling depends on the thickness and height of the barrier, as well as the energy of the particle. Thicker or higher barriers make tunneling less likely, but even the tiniest probability can lead to significant effects when dealing with vast numbers of particles, as happens in stars and certain technologies. What's even more fascinating is how tunneling challenges the classical notion of impenetrable barriers. In classical physics, a barrier is either penetrable or not, depending on the energy of the object. Quantum mechanics introduces a world where possibilities aren't so rigid. Instead, they're dictated by probabilities. Even the most solid walls might not be as impenetrable as they seem. Tunneling also forces us to think differently about energy conservation. How can a particle borrow energy to get past a barrier and still respect the laws of physics? The explanation lies in the fact that quantum mechanics allows temporary violations of energy conservation. As long as they occur over very short time scales, this is a consequence of the Heisenberg uncertainty principle, which tells us that we can't precisely know both the energy and time for a quantum event. So a particle can briefly borrow energy to tunnel through, as long as it gives it back right away. Can you imagine a world without quantum tunneling? Many of our modern technologies would be impossible. Consider the development of semiconductors, the materials used in computer chips. Tunneling affects how electrons move in these materials, making it essential for the operation of transistors, which are the building blocks of all modern electronics. Without quantum tunneling, we wouldn't have the computers, smartphones, or countless other devices that are now part of everyday life. Yet, the implications of tunneling go beyond technology. It raises questions about the very nature of reality. If particles can pass through barriers based on probabilities, does this mean reality isn't as fixed as we think? What if our understanding of boundaries, both physical and conceptual, is limited by the quantum rules that govern everything at its most fundamental level? Some scientists even speculate about how tunneling could be related to the origins of the universe. Quantum tunneling may have played a role in the early universe's inflation, a period of rapid expansion. This idea is still theoretical, but shows just how deeply tunneling is woven into the fabric of our understanding of reality. As strange as quantum tunneling sounds, it's a reminder of how different the quantum world is from our everyday experience. We live in a world that seems predictable and solid, but beneath the surface, there's a realm where probabilities rule, and particles can do things that defy our intuition. Does this mean the universe itself is full of surprises? It certainly seems that way. Quantum tunneling also highlights the need for a deeper understanding of the connection between the quantum and classical worlds. How do these two realms coexist? Why do quantum effects like tunneling become negligible on larger scales? These are questions that continue to puzzle and fascinate physicists. pushing them to search for new theories that can explain the quantum world's mysteries. So the next time you think of a wall or a barrier, remember that in the quantum world, nothing is quite as definite as it seems. Even the most solid structures may have quantum secrets waiting to be discovered. How certain are we about what we know in our daily life? If we measure a cup's volume or a car's speed, we expect precise numbers. But in quantum mechanics, certainty isn't so simple. Have you ever wondered if we could know everything about a particle's state with absolute precision? The Heisenberg uncertainty principle tells us otherwise. So what exactly is this principle? It states that we can't know both the exact position and the exact momentum of a particle at the same time. If we try to pinpoint a particle's position with extreme accuracy, our knowledge of its momentum becomes uncertain and vice versa. This principle isn't just a limitation of our measuring tools, it's a fundamental feature of the quantum world. Imagine you're trying to measure a tiny particle, like an electron, if you want to see exactly where it is. You have to use light or some kind of wave to observe it, but the smaller the particle, the higher energy you need for this wave. When you hit the electron with a high-energy photon, it changes the electron's momentum. It's like trying to take a close-up photo of something delicate. The act of taking the photo ends up disturbing the object. So even before we attempt to measure, the very act of observing introduces uncertainty. But why can't we escape this limitation? To answer this, think of the wave-like nature of particles. An electron isn't just a point in space, it's described by a wave function, a mathematical description that gives the probabilities of where the electron might be found. If the wave is very spread out, the particle's position is uncertain, but its momentum is more definite. If the wave is tight and localized, the particle position is clear, but the momentum becomes uncertain. The more we narrow down one of these aspects, the more the other blurs. How does this uncertainty affect our understanding of the universe? It challenges the classical idea that everything follows precise, predictable paths in the everyday world. We assume that if we know where something is and how fast it's moving, we can predict where it will be in the future. But in the quantum world, this kind of precise prediction is impossible. Instead of certainty, we deal with probability. This change from a deterministic to a probabilistic view is profound. For instance, when we talk about an electron in an atom, we can't say for sure where it is. We only know the probability of finding it in a certain region. The uncertainty principle plays a crucial role in the structure of atoms. If electrons could have both a well-defined position and momentum, they would spiral into the nucleus, and atoms as we know them wouldn't exist. Instead, the uncertainty principle keeps electrons spread out and stable, forming the atoms that make up everything around us. You might ask, does this uncertainty apply only to the microscopic world? It does, but it's so small that we don't notice it on larger scales. For example, when we talk about a car or a ball, the uncertainties in position and momentum are so tiny that they're irrelevant. The classical world seems predictable because the quantum uncertainties average out. Now let's dive into the probabilistic nature of quantum mechanics. Unlike classical physics, which deals with definite outcomes, quantum mechanics describes reality in terms of probabilities. Instead of asking where a particle is, we ask where it is likely to be. When we make a measurement, we don't find the particle in several places at once. Even though its wave functions spread across different locations, we find it in a specific spot. The wave function collapses to reflect that. This brings up a big question: why does the wave function collapse when we measure it? No one knows for sure. This idea of collapse is one of the most mysterious parts of quantum mechanics. For measurement, the particle exists in a superposition of all possible states, but the moment we observe it, the wave function suddenly decides on a specific outcome. Does the active measurement cause reality to become definite, or is it something else entirely? Another way to think about quantum uncertainty is by looking at the position and momentum of particles. If you could know an electron's exact speed, you wouldn't have a clue where it is. If you tried to pin down its exact location, you'd lose all information about how fast it was moving or in what direction. These are not just measurement problems. They reflect the limits of what nature allows us to know. To illustrate how quantum uncertainty can seem strange, consider an experiment where we shoot electrons through a narrow slit. As we make the slit, narrower to get a better idea of the electron's position. The uncertainty in its momentum grows. This increased momentum uncertainty causes the electron to spread out and travel in unpredictable directions. In other words, trying to make one thing certain creates more uncertainty elsewhere. What does this probabilistic nature mean for the world we live in? It suggests that at its core, reality might not be as fixed as we think. Classical physics assumes that everything has a definite state at any given time, even if we don't know it. Quantum mechanics challenges this view, proposing that particles don't have definite states until they're measured. Until then, they exist in a blend of possibilities. If quantum mechanics is all about probabilities, how does it impact things like energy levels in atoms? It turns out that energy levels are also subject to uncertainty. Electrons and atoms have quantized energy levels, meaning they can only exist in specific energy states. But even within those states, there's a small uncertainty in energy. This energy uncertainty becomes significant in quantum phenomena, like virtual particles popping in and out of existence. An idea connected to the uncertainty principle. Does the uncertainty principle mean that everything is unpredictable? Not quite. While individual particles behave unpredictably, the behavior of large groups of particles becomes predictable. That's why classical physics works so well for everyday objects. The uncertainties of countless particles average out, giving us a world that appears certain and follows clear rules. Quantum uncertainty also plays a role in advanced technologies like transistors. Transistors control the flow of electrons, and quantum effects like tunneling depend on these principles of uncertainty. Understanding quantum mechanics is crucial for designing smaller and more efficient electronic devices. The Heisenberg uncertainty principle and the probabilistic nature of quantum mechanics also lead to philosophical questions. If we can't know everything about a particle's state, does that mean the universe is inherently unpredictable? Or are there hidden variables we haven't discovered yet? Some physicists have proposed theories that introduce hidden variables, but so far, these ideas haven't provided a clearer picture of quantum uncertainty. As we keep exploring these concepts, one thing is clear: quantum mechanics shows us a world full of possibilities. The certainty we're used to in the classical world doesn't apply to particles at the quantum level. Instead, we are left with a reality governed by chance and probabilities. The mysteries of quantum mechanics continue to challenge our understanding, pushing us to think beyond what seems obvious. Does this mean we'll ever fully understand the universe's fundamental nature? It's hard to say, but the journey of discovery is what makes science so exciting. And as we learn more, the line between what we know and what we can never know keeps shifting, revealing a world more complex than we ever imagined. Let's start with a question: how does reality work if particles behave unpredictably at the quantum level? Quantum mechanics offers several theories to explain how particles interact and behave, each trying to address the strangeness of the quantum world. One of the most discussed is the Copenhagen interpretation. What does the Copenhagen interpretation say? This approach, introduced by Niels Bohr and Werner Heisenberg, suggests that quantum particles don't have definite properties until they're observed or measured. Until we observe them, these particles exist in a state of probabilities. When a measurement is made, the wave function describing all possible states collapses into one actual outcome. This view is strange. Imagine you're looking at a ball. In the classical world, the ball has a definite position and speed whether you're observing it or not, but in the quantum world, a particle like an electron only decides on a position or speed when you measure it. Before that, it's like a mixture of all possibilities. So does reality depend on observation? Does something only become real when we look at it? Let's think about Schrödinger's famous thought experiment. In this experiment, a cat is placed inside a box with a quantum device that has a 50-50 chance of killing the cat based on the behavior of a subatomic particle, according to the Copenhagen interpretation. Until we open the box and observe the situation, the cat is both alive and dead. Only when we look inside does the wave function collapse, and the cat's fate becomes real. It's as if nature waits for our observation before deciding what's true. Isn't that bizarre? It makes us question the nature of reality itself. But not everyone is satisfied with this explanation. In fact, the Copenhagen interpretation has sparked endless debates. How can something not be real until it's observed? This leads us to our next question. Are there other theories that make more sense? One such alternative is the many worlds interpretation proposed by physicist Hugh Everett. Instead of particles choosing one outcome when observed, this theory suggests that every possible outcome of a quantum event actually happens. When you measure something, the universe splits into parallel versions of itself, each reflecting a different outcome in one universe. Schrodinger's cat lives in another. It doesn't, so do we live in a multiverse of branching possibilities. The many worlds interpretation suggests that every time a quantum choice is made, a new reality forms. Think about the consequences of this. Every decision, every random event creates a new universe. It sounds like science fiction, but some physicists take it seriously. Yet there's a big problem. If all these worlds exist, why can't we detect them or move between them? The idea of parallel universes is mind-boggling. However, the many worlds interpretation does solve one problem. It gets rid of the idea of wave function collapse instead. The wave function continues, and all possibilities become real somewhere. But if that's true, does it mean there are infinite versions of you, each living a different life? The theory raises as many questions as it answers. What about theories that bring back a sense of certainty, like the pilot wave theory? This theory, first proposed by Louis de Broglie and later developed by David Bohm, reintroduces a kind of determinism to quantum mechanics. According to the pilot wave theory, particles are guided by an invisible wave called a pilot wave. This wave determines the path of the particle, making everything predictable if we knew all the details. Unlike the Copenhagen interpretation, the pilot wave theory suggests that particles always have definite properties even when they aren't being observed. The wave function isn't about probabilities, but is an actual wave influencing the particle's motion. Does this make quantum mechanics less mysterious in some ways? Yes, but it still doesn't explain everything. For example, the theory still has to account for the wave-like behavior of particles and match experimental results. If particles always have definite states, why don't we notice this in our measurements? One reason is that the pilot wave remains hidden, making it hard to distinguish this theory from others. The pilot wave theory challenges mainstream views, but doesn't have enough experimental evidence to fully replace them still. It keeps the debate about quantum mechanics alive, offering an alternative view of reality. With so many competing interpretations, how do we decide which one is right? The truth is we don't have all the answers yet. Quantum mechanics works incredibly well for calculations and predictions, but it leaves us with a deep puzzle of the nature of reality. Some physicists believe we need a completely new theory to make sense of it. All others think we should just accept the weirdness. Let's discuss one more question. How do these interpretations impact our understanding of the universe? If reality depends on observation, does that mean the universe needs an observer to exist? Or if there are infinite parallel worlds, what does that say about free will in our choices? And if a hidden wave guides everything, does that mean the universe is ultimately deterministic? These theories show that our classical view of a predictable concrete world doesn't apply at